Hi everyone, welcome to my office hours. Today I'll be going into chapter 6, which is just an overview of different organic reactions, and going into chapter 7, which is specifically about substitution reactions. Personally, what I think is the most important part of chapter 6 is understanding how the energy diagrams work as far as transition states, intermediates, reactants, products, and how many steps it goes. So if we compare these two energy graphs here, we can see that this guy is 1 step and this guy is 2 steps. Because this one only has a single activation energy to go over, which means it only has a single reaction to go over. However, this one has 2 activation energies, which means it has 2 steps in its process, which means it's going to be a stepwise 2-step reaction. In addition, it's important to be able to recognize what is a transition state and what is an intermediate. And somebody in chat asked, can you also say the amount of steps is equal to the amount of transition states? Yes, you can, because that is inherently have to do with the activation energy, exactly. So the main difference between transition states and intermediates is that transition states have partial bonds. So we can see here that in this transition state example, we can see here that it has a partial bond here and a partial bond here, which is represented by these dashed arrows. However, when we're talking about intermediates, like this one right here, we only see full bonds, okay? We see full bonds and no partial bonds between the chlorine and the bromine and the carbon in the center. So that's the main difference between transition states and intermediates. Intermediates actually exist between these 2 reactions. So we see here 2 activation energies, we have 2 reactions. For the first reaction, these 2 reactants are our reactants. That was sort of weird to say. What I mean is in the actual reaction, we focus on this guy right here, and then in the second reaction, we're focusing on using the intermediate as the reactants. So if I were to draw this reaction out, I would first draw, let me move some stuff around, I would first draw the alkyl halide, which again is just an alkyl group, which is a carbon-hydrogen group, with a halogen, which is a halide group, on there. And so then this is the first step. The first step is the bromine breaks off, and we get a carbocation intermediate. And then the chlorine comes in, and it replaces where that bromine was, and we get this guy right here, okay? And so we can see here we have 1 step and then 2 steps. In step 1, this is the reactant. In step 2, both of these are the reactants, okay? And this will become more important when we're talking about substitution reactions. If you are already familiar with that, you'll be able to see that this is an Sn1 reaction, but we'll discuss this more in depth later, so don't worry about it too much if you don't understand it right this moment. Also, when we're looking at energy graphs, or free energy graphs there rather, we have to be able to tell if a reaction is endergonic, also known as endothermic, or exergonic, which is also known as exothermic. So essentially what each of these means is, again, this is some terminology from your Gen Chem stuff, so you should have like a basic idea of what this means. Endergonics means we're putting energy in. So free energy, delta G, or I guess not delta G, but G is gonna go up. Exergonic, we're giving off energy, so G is gonna go down. In this example here, we can see that G, which is on the y-axis here, went from up here to all the way down here. We got rid of energy, it was released, so this is exergonic, whereas instead of maybe having a reactant right there, or a product right there, we have a product right here. We can see that G went from here to here, and G went up, so this would be endergonic. Again, this is sort of a review from Gen Chem. But if I were to give you like a question that could be asked, it would be like, if I said this reaction has 2 steps and it's endergonic, you should be able to tell that here's our G, here's our reaction coordinate. You should be able to tell that if I said it was endergonic, our reactants will be here, our products will be up here, and I said it was 2 steps, so I'd have 2 activation energies, and I'd go like this. Oh, sorry, let me draw that a little bit better. Like this, okay? Somebody asked, so when the products are lower than the reaction, or when the products are lower than the reactants, the reaction's exothermic. Yes, exactly. You can think of it as this graph is showing us the reaction, the energy in the actual reaction. So you can see here in this example here, we said this was endergonic. In the actual reaction, we had to put in energy to get up to this point here. In this other one, like right here, we saw that the reaction lost energy. That energy had to go somewhere, so it was just released. Okay? Does that all make sense to everybody? Oh, and what differentiates between a slow and fast exothermic reaction? So when we're comparing the quote-unquote fastness of reaction, the speed of a reaction, it depends on a couple of things. But for our class, what we're going to be mostly looking at is the exergonic. Yeah, exergonic. We're going to be looking at the activation energy. So let's compare these two reactions right here. We can see that this one has a much higher activation energy, so it has a much higher energy barrier to go over, so it takes longer to get that energy. And then here we can see here that it has a lower activation energy, so it's generally going to be faster. One exception to this is if you had an enzyme or a catalyst, which would lower the activation energy. So let's say that we had a catalyst that lowered the activation energy to right down here, then this one will be faster. But that's only when we add a catalyst. Does that make sense? I think I answered that question. All right, perfect. So just to reiterate, usually the activation energy is going to determine how fast a reaction is going to go. And then when looking at a case like right here, where we have two steps, we have quote unquote two activation energies. Our first activation energy is when we go from reactants to this transition state. So here's our activation energy. However, our second activation energy does not start with the reactants. Instead, it starts with the intermediates. So we're going from here to here. So you can see that this second reaction is much faster than this first one because the activation energy is much lower. So if I were to ask, oh, which is the slow, which is the fast step here, I would say this first step is the slow step because the activation energy is so much higher than the second step. All right? Okay. Okay, so one more thing I want to talk about a little bit more there are a few more things I want to talk about more in depth in this chapter, but the first thing I want to talk about is the difference between a kinetic product and a thermodynamic product. So let's say that we have a reaction, A plus B, and it can either create the products E plus F or C plus D, okay? And actually, let's not use this graph right here. Let's use the next one. So again, same situation. A plus B can either make E plus F or C plus D. And we call these two products either the thermodynamic product or the kinetic product. The kinetic product is generally which one's going to be formed the fastest. And then the thermodynamic product is whichever product is the most stable. So how do we tell if something's more stable than the other? Well, generally, if something is lower energy, like C plus D is here, than E plus F, it's going to be more stable. So C plus D here is going to be our thermodynamic product because it is more stable. On the other hand, E plus F is going to be our kinetic product. Because it has a lower activation energy, it's going to form faster and be the kinetic product. In our class here, we don't, at least in Orgo 1, we don't talk about many reactions that can form both a kinetic and a thermodynamic product. It's just important to be able to tell these two apart if given an energy graph like this. In Orgo 2, you'll be talking a lot more about different kinetic and thermodynamic products. Okay. And so let's continue on. You may notice I'm going a little bit backwards. That's because I like to talk about an energy diagram first before going into these other reactants. So now let's talk about kinetics. So kinetics is how, quote unquote, fast something's going to happen, the rate of the reaction. And this reaction, or this equation rather, is going to be very important going on into Sn1 Sn2 substitution reactions, and then further past this second test to elimination reactions. So I personally think that this is one of the more important equations that we cover in this chapter, mainly because we're talking about first order versus second order versus third order. So how do we tell if something's first order, second order, or third order? All we do is we add up the different exponents. So we can see here that this guy looks like he has no exponents, but there's a hidden exponent 1 here. And same here and here. So this one's first order because it only has 1 as an exponent. 1 plus 0 is 1, first order. Second order, 1 plus 1 is 2, second order. And then here, 2 plus 1 is 3, third order. Okay? And this has to do with naming stuff later, like naming certain reactions. It's just important to be able to know, like, if we have a rate, to be able to tell how to calculate that. So now let's say we have our energy diagram here. Let's say we have our reactants here, our intermediates here, and then our products right here. So when I look at this graph, I should be able to immediately be able to tell that this is exergonic, and it's a stepwise reaction with 2 steps, okay? And now what I'm going to do is I'm going to find the rate determining step. In this case, it's pretty obviously going to be the first step. So our first step is rate determining. And so then both of these different steps have a rate equation. However, the rate equation that determines the overall rate is going to be our slow step. So the first step, since it's slower than the second step, is going to determine the rate of our whole reaction. Okay? Does that make sense so far? Okay. So let's say that in our first reaction, we have A plus B, or our reactants are A plus B, and then our intermediate is C. We can have 2 rate equations where R equals K, which is a constant, so don't worry about memorizing that. The concentration of A times the concentration of B, and then the rate of the second step is just going to be K times the concentration of C. So now when we look here, we can see that the first rate is going to be second order, and the second rate is, or the second rate, yeah, exactly, is going to be our first order. But which one determines the rate of the reaction? It's going to be our first one. So overall, this whole reaction is going to be second order. Okay, and it'd be the same thing if I did it backwards. Like, let's say that instead of this was A plus B and this was C, that this was C and this was A plus B. Then and then rate 2 would determine our rate of our overall reaction. Okay, it just depends on which one is going to be our slower step. Okay, so let's continue on. Okay, so these couple of equations, I wouldn't worry about too much unless you're going on to the MCAT and stuff. You don't really need to memorize them for this class specifically. Like this KEQ, it's important to know, but not for a test. And then here, when we're talking about delta G, this whole equation is really, really scary. But for our purposes, delta G roughly equals delta H. And all this is the heat or the energy within our reactants and our products, which again, we described using our energy diagram or energy graph, where this was delta G. And again, remember, delta G is roughly delta H, okay? So if instead, like let's say on a test, that instead of having delta G on the y exponent, you have delta H, we said that delta H is roughly equivalent to delta G, so that really won't change anything. Okay, I know that sometimes confused people a few semesters ago. And so then, yeah. So entropy, delta S, again, we don't talk about this too much because we're more concerned with enthalpy. But just to reiterate, in case there's like a question about this, entropy is essentially the order of chaos within a system. So we can see here that we start over here with 2 moles of reactants. So like we can say we have 2 units of chaos. And then here we go into 1 mole of reactant. So we only have 1 unit of chaos. So our chaos goes down, our delta S goes down. Okay? Okay. So let's continue on just one more thing. I just want to go over one more thing because I did go over the difference between addition, substitution, elimination, all that stuff last week. So I just want to reiterate, because this is going to be important for the next chapter, how arrow pushing mechanism works. So there are 2 types of ways that we can break a bond. We can either do it equally, where each atom gets a single electron, and we create something called radicals, okay? Radicals are just essentially atoms or molecules even with only an odd number of electrons. So CH3 with a single electron, that's considered a radical. whereas we can see CH3 with 2 electrons is negatively charged, and CH3 with no extra electrons is positively charged. These two are ions. This is a radical, okay? And radicals are formed through homolysis. Homolysis is when a bond breaks and each part of the bond gets 1 electron. They're shared evenly. On the other hand, there's heterolysis. Heterolysis is what we're going to be talking about in the next upcoming chapters. Homolysis comes up in later chapters such as radical reactions. Okay? Heterolysis is when a bond breaks and all the electrons go to one side or the other side of the bond. So in this case, all of our electrons went to B and we made 2 ions. Heterolysis makes ions. Okay? All right. So now how do we draw this breakage of bonds? So when we're drawing the movement of electrons, which is, oh, I'm sorry, I just saw there was a question in chat. And somebody asked, so when moles increase from reactants to product, delta S is greater than 0, and when they decrease, delta S is less than 0, and when they stay the same, S is equal to 0. Exactly, that's exactly right. So going back to what we were talking about earlier, we're talking about delta S, is if we start with 2 moles and we end with 2 moles, delta S is 0 because nothing changed. If we start with 2 moles, we end up with 1 mole, delta S is negative. And then if we start with 2 moles and end up with 3 moles, then delta S will be positive because chaos is going up in this case and chaos is going down in the previous case. You're totally fine. Okay, I hope that answered your question. Back to heterolysis, homolysis, I mean. So essentially, when we draw arrows, we draw the movement of electrons, and that's why we're starting from a bond here. The only place in this diagram, I guess you can call it a diagram, with electrons is that bond, so we draw the arrow from the bond. In addition, the arrow is going from where the electrons start to where the electrons end. So here, all the electrons end up at B. And finally, we're talking about an arrow that's holding on to 2 electrons. So that means we're going to be using a full-headed arrow. I like to think of each side of the arrow holding 1 electron. So if I have a full-headed arrow, I'm moving 2 electrons. And on the other hand, when I have a half-headed arrow, it's only able to hold on to 1 electron. So you can see here, we have 2 arrows from either side, with each with 1 electron, so they're half-headed, breaking the bond evenly. And here on the other hand, we see, in the other example here, we see a full-headed arrow moving 2 full electrons. So that's heterolysis, okay? And so then one more thing. Here's another example of how arrows will move. We can see here in the bond forming of 2 radicals, the 2 electrons meet in the middle because we can't exactly say the electrons are going anywhere because we can't say that B is moving 1 electron to A and A is moving 1 electron to B. It's more correct to say that the 2 electrons, or 1 on each atom, are coming together to make 1 full bond, so they come to the center here. On the other hand, when we have 2 electrons here, we can sort of say that these 2 electrons are being donated to A in order to make a new bond, because A did not have any electrons to start with, so it has no way to make a bond. So all of the bond has to come from B and go to A. Okay, and so then that's the basis of mechanisms or arrow pushing mechanisms. And one more thing, the arrow pushing mechanisms are going to be used a lot more in further chapters. And the arrow pushing mechanisms show the movement of electrons and not atoms. They're generally going to go from either a bond or a lone pair to an atom or to another bond. Okay? Okay. So are there any questions about chapter 6, or can I just move straight on into chapter 7? All right. I'm just going to go on to chapter 7. If anybody has a question in chat, I will move back and talk a little bit more about chapter 6. But let's talk about alkyl halides and substitution reactions. So when we're talking about substitution reactions, we're going to be talking about alkyl halides, which is why this chapter is sort of squished together. So alkyl halides are basically made up of 2 parts. The alkyl group, which is just made up of C's and H's, and then the halide group, which is just a halogen. And if you recall, the halogens are F, Cl, Br, and I, if I'm doing that in the right order, I think. And mainly, And this is what we're going to be talking about this entire chapter. So this X can be replaced by any one of these 4 halogens, okay? And so when we're talking about naming alkyl halides, they're super easy. All we do is we do the same thing that we were before, is where we number our parent chain 1, 2, 3, 4, 5, 6. We see where our substituent, in this case a halogen, is on our parent chain. So in this case it'd be like 3. I think I numbered the wrong way, but just bear with me. So in this case it'd be 3, and then all we do is we say 3 bromo, or 3 iodo, or 3 fluoro, or 3 chloro. Honestly, it's really easy. Just one thing to look out for is if, like, let's say, for example, that I have something like this. 1, 2, 3, 4, 5, 6, 7, 8. So let's say I have something like this, and I have BR right here, and I number it. I have 1, 2, 3, 4, 5, 6, 7, 8. I have an octane, and I have a bromo on 3. So our answer would be 2 bromo octane. Note how I did not drop an O here, okay? This is a mistake I see a couple times. These 2 words are completely separate, so you're not gonna drop any O's or any letters from any name, okay? So that was a good example. I'm just gonna continue on because I feel like naming alkyl halides is going to be not that hard, especially when compared with other parts of this chapter. So I'm just gonna continue on. But if you do want me to go back and talk about it more, I'm totally willing to do that. Just let me know. Okay, so those are alkyl halides. What we're most interested in alkyl halides is how, at least for this chapter, is how they do nucleophilic substitution. All this means is a nucleophile, which means nucleus loving, attacks this alkyl halide, replaces the halogen with the nucleophile, okay? And notice in this case here, nucleophiles and bases are different, but generally, if you have a nucleophile, it's gonna be a base. So for example, OH negative, a well-known base, is a nucleophile, okay? But not all bases are nucleophiles. It just depends on a couple of factors that we'll talk about a little bit later. It's just to clear up here that nucleophiles can be bases. Don't get these mixed up too much, okay? Okay, so let's continue on. So when we're talking about replacement reactions, which means substitution reactions, what happens here? We can see that in every single case, a bond is broken. Oh, somebody asked in the chat, so are nucleophiles always going to have a negative charge? No. They can be a nucleophile as long as they have an available electron pair and they aren't sterically hindered. Again, I'll talk about steric hindrance a little bit later. So H2O can be a nucleophile, a weak nucleophile, but it's still a nucleophile. In the same way that OH is a nucleophile, but it's a strong nucleophile. Generally, you'll see weak nucleophiles being neutrally charged and strong nucleophiles being negatively charged, other than nucleophiles that are negative, or bases that are negatively charged but very sterically hindered. Again, we'll talk about that later. I think I answered your question, so I'm gonna go ahead and move on just to this next bit. Okay, perfect. We can see here that 2 bonds are changed. So we broke this bond and we formed this bond, okay? So if I were to draw the arrow pushing mechanism, I would have to think about it a little bit, because I see here that this carbon in the center, it can't have more than 8 electrons around it, okay? But we can see here that it does not have a charge, so it's implied that it already has a 4th bond as far as hydrogen goes, okay? So what do? Well, I break this bond and I break it so all of the electrons go onto X, so whatever halogen we have, and that is because, again, the carbon cannot have more than 8 electrons, okay? So like, for example, this is wrong, but if I put the electrons from this bond going onto this carbon here, it would have no place for these electrons from the nucleophile to grab onto, okay? So I have to draw this bond breaking and all the electrons going to X, okay? So that's one bond taken care of. Now the next bond we need to focus on is the bond between the nucleophile and the carbon. All that happens is the nucleophile takes its extra electrons and then attacks that carbon right there with them, making that new bond, okay? And so we can see this happening in these other examples here. So we can see here, this carbon-chlorine bond breaks for this carbon OH bond to form. This carbon iodine bond breaks for this carbon SH bond to form, and so on, okay? So that is the general mechanism for substitution reactions. There are a few things that change, though, when we're talking about the two different kinds of substitution reactions. So there are two different kinds. There's Sn1 and Sn2. So the main point of contention with Sn1 and Sn2 is sort of why they're named what they're named. Because Sn1, it is two-step substitution, whereas Sn2 is one-step substitution, which doesn't seem to make much sense. But it makes a little bit more sense when we talk about what is happening when we do the substitution. So let's take two examples of let's take one example for Sn1 and one example for Sn2. For Sn1, the first step involves this carbon leaving, or this halogen leaving the carbon, and we end up with a carbocation. This is our intermediate. So we call it an intermediate carbocation, and again, a carbocation is just a carbon with a positive charge. Whereas in Sn2, everything that happens at once. The carbon bond breaks, and then the nucleophile bond is formed. So this is all in one step, and we end up with our new product, okay? But in this one here, we have a second step where the nucleophile attacks after the carbocation is formed. Notice here how the arrow movement is essentially the exact same thing. It's just for Sn1, oops, that shouldn't be next, that should be nucleophile. For Sn1, it takes just one step longer, okay? So I'm going to erase this. So now let's look at Sn1 and Sn2 by comparing their reaction graphs. So this is something that we talked about in chapter 6. So we say that Sn1 is two steps. So it's going to have two activation energies. So 1, 2. Sn2 has only one step. So we have one activation energy, 1. Okay? So notice here that in Sn1, we start with the alkyl halide, which then becomes our carbocation, which then becomes our product with the nucleophile, okay? Sn2, we start with both the product and the nucleophile, and we end up with our new product and the extra halogen, okay? Notice here how this guy starts out with a single reactant. This one starts out with two reactants. So if we look at the rate equations for both of these, we can see that the rate for Sn1 equals K times the alkyl halide, which I'm going to abbreviate AH. And Sn2, we have R equals K times the alkyl halide and the halogen, or I mean, sorry, and the halogen, and the nucleophile, which I'm just going to abbreviate NUC. Okay? So notice here that Sn1 is a first order equation and Sn2 is a second order equation. That's where the name comes. Sn1 is first order, Sn2 is second order. Sn1 is two steps, Sn2 is one step. Okay? So that is the main difference between the two of them. So now we're going to talk about how do we know it's going to be Sn1 or Sn2? Because they generally come out with similar products. It's just Sn1 happens in two steps, Sn2 happens in one step. There are generally 4 factors that affect substitutions. The one that probably affects Sn2 versus Sn1 the least is the leaving group. So I'm just going to go ahead and skip down to that right now. So leaving groups are essentially defined by how good they are at leaving. Surprising, I know, but you can think of leaving groups as sort of analogous to our acid-base reactions. Remember we talked about how the more stable the conjugate base was, the better the acid was. Oops, I guess I skipped past it. It's the same concept here. The more stable the leaving group is on its own, the better it is at being a leaving group. So if we compare, I guess, okay, so I'm just going to do it right here. So if we compare fluorine versus chlorine, if we use the same rules that we talked about in acid-base reaction, we can see that chlorine is bigger, so it's going to be the better leaving group. So if I were to put these in order, fluorine is the worst leaving group, followed by chlorine, followed by bromine, followed by iodine, okay? Because these are halogens, this is what we're going to be talking about the most. However, there are different leaving groups that we will discuss a little bit in this chapter. These are the main big ones. Like if I were to ask you what would make a good leaving group, you would say iodine or bromine or something. But there's also other ones, like let's say that we had this guy versus this guy. Which one has the better leaving group? All we do is we look at the quote-unquote conjugate base. You look at OH negative versus NH2 negative. Which one is more stable? Well, we look at the atomic effects. We see here that O and N are the same size, but O is more electronegative, so it's going to be more stable. So this one has the better leaving group, and you would just do that with all of the other, you would just follow these trends with everything else. So this is where acid-base ideas come back into play. And again, like I said before, the better the leaving group, it doesn't matter so much whether it's going to be Sn1 or Sn2. All it means is the better the leaving group, the faster the reaction is going to proceed. So like, let's say I have this guy versus this guy. This one is going to have a faster substitution reaction because the leaving group is better, okay? And again, the leaving group does not determine whether something's going to be Sn1 or Sn2. For both of those reactions, a better leaving group means an increased reaction rate, okay? So now let's talk about what actually makes Sn1 and Sn2. Well, again, like we said before, Sn1 and Sn2 are defined by one of them being one step, one of them being two steps. And when we look at Sn1, we can see that it creates a carbocation. So let me just draw an example here. So the carbocation stability very strongly affects whether or not something's going to be Sn1 or Sn2. And when we're talking about carbocation stability, the general rule of thumb is that the more substituted the carbon is, the more stable it is. So let's compare this guy to this guy. So we see here, this is a primary carbon with a positive charge. This is a tertiary carbon with a positive charge. So this one's going to be more stable overall, okay? So the general order of stability for carbocations goes a methyl carbocation, which is just a single carbon with no other carbon attachments, is less stable than a primary carbocation, which is less stable than a secondary carbocation, which is less stable than a tertiary carbocation, which is our most stable carbocation. Oh, I said carbocation a lot there. But so when we're talking about Sn1, it's going to prefer the tertiary carbocations the most. So Sn1 loves tertiary carbocations. And on the opposite side of the spectrum, Sn2 prefers the least substituted carbocations. And you might be wondering why that is. Well, one of the things about Sn2 is it wants to go as fast as possible. So it wants to have as much room to attack that carbon that the leaving group is on as it can. And if it is being blocked by a bunch of bulky tertiary bases, or tertiary, if it's being blocked by a bunch of different carbon bits attached to that carbon right there, it's going to have a really hard time attacking. So again, Sn2 wants speed, so it wants to have the carbon as accessible as possible. So Sn2 prefers methyls over tertiaries, over secondaries, and it almost never does Sn2 with tertiaries, okay? All right, so that was talking about the substrate. So now let's talk about the nucleophile. So for Sn1, again, remember that it likes to form its carbocation first. If it has a really, really strong nucleophile, that nucleophile is going to try and attack before that carbocation is formed. So Sn1 prefers weaker nucleophiles. So weaker nucleophiles on this side of the of this chart here. And on the other hand, again, Sn2 is all about speed. So it's going to prefer the stronger nucleophiles to attack as fast as possible. Now, there's one more thing to note here, which I'm going to get into, is you can be a base, but not a nucleophile, okay? And this occurs due to steric hindrance. Steric hindrance is essentially just a bunch of stuff getting in the way of the nucleophile to attack. So the way that I like to describe it is, let's have these two bases here, and I ask you which one is a better nucleophile. The way that I like to think of it is the nucleophile wants to go and attack the parking space that the leaving group was in. And we can consider this guy here a tiny little bug car, and this guy a big truck. The bug car is going to have a lot more advantage getting into that small spot than this big truck here. So this is going to be the better nucleophile because it has better access to the carbon that it's replacing the leaving group from. Okay? I know a lot of people have issues with that. And so if I were to ask you, order these in order of nucleophilicity, what you would do is you would just see which one is the most substituted. That means it's going to have the most steric hindrance. So this guy here is the most substituted, so it's going to be the worst. So if I'm rating these from best to worst, this is going to be number 3. And then I'm comparing these two. Well, I see that this one on the right is a primary carbocation, and this one is just a methyl carbocation. Or I'm sorry, not carbocation, a methyl carbon. So this one's a primary carbon, this one's a methyl carbon. This one has more stuff, more steric hindrance, so it's a worse nucleophile than this guy. So this one is the best nucleophile, this one's the worst, and then this one comes in the middle. Okay. Oh, and those nucleophiles, those or the sterically hindered bases, they're still bases, they're just not nucleophiles. And so we call these strong bases weak nucleophiles or non-nucleophilic bases. Okay? So now we're going to be talking about solvents. So we are going to be mostly talking about polar solvents instead of non-polar solvents. And the two big categories of solvents we're going to be talking about is protic solvents and aprotic solvents. What protic solvents means, it means it has some degree of hydrogen bonding. So it has an OH, NH, or an FH somewhere in it. So this would be a protic solvent, this would be a protic solvent, and so on. Just if you see an OH, it's going to be protic. And so what protic solvents do is they really isolate stuff. So let's take the example of water. H2O. When we look at H2O, we can see that each H has a partially positive charge and the oxygens have a partially negative charge. And this has to do with the electronegativity of the oxygen being much greater than the hydrogen. So we can say that water is made up of a bunch of partially positive and partially negative charges. And so what happens in a reaction is that in a protic solvent, all of the positive charges, or all the partially positive charges, are going to work to surround any negative charge. Now, on the other hand, any negative or partially negative charges are going to work to surround any positive charge. In this way, both of these charges are completely separate, okay? And so we can sort of think of this negative charge as our nucleophile. And then we can think of this positive charge as whatever our substrate was. Oops, that's not lemon. So I'm gonna designate our substrate as Rx, where R is the alkyl group and X is our leaving group. So in this case, the nucleophile and the alkyl, or not the alcohol, the alkyl and the leaving group are very separated. So this guy has a lot more time to form a carbocation, okay? So since these guys are separated, there's more time for that second step to occur. So protic solvents prefer Sn1, okay? On the other hand, you can probably assume that polar aprotic solvents don't separate everything fully. On the other hand, they sort of separate things partially. So they may separate, I don't know, the nucleophile a little bit more, but they will not separate that alkyl and the leaving group. So the nucleophile is going to have a lot easier time of attacking in an aprotic solvent So this one serves itself to not forming a carbocation and instead forces it to be Sn2. Okay? All right. So those are the solvents. The last thing, again, we already talked about nucleophilicity. We already talked about the leaving group. We talked about the protic solvents, and we talked about the how the substrate affects it. So I'm going to make a nice little chart right here, and we're going to compare Sn1 to Sn2. So Sn1 versus Sn2. So to summarize, Sn1 is 2 steps, where I'm just going to draw Rx, where X is the leaving group, and so then it leaves, and we get a carbocation, R+, and then the nucleophile attacks, R+, and then we end up with our substitution, our substituted product, which is going to be R nucleophile, okay? Sn2, on the other hand, is 1 step. So all of this stuff happens in 1 step. So Rx and the nucleophile all react in 1 step. So the leaving group leaves and the nucleophile attacks, and we end up with a R nucleophile bond. Okay? So here's the summary of Sn1, Sn2. Again, Sn1 is first order and Sn2 is second order, which is why we call it that. And so now let's get into when are we going to do each of these? Well, Sn1 is going to occur more often if we have a tertiary carbon, a secondary carbon over a primary carbon, and it almost never happens with methyl carbons. Okay? Sn2, on the other hand, happens a lot more with methyl than primary, than secondary, and almost never happens with tertiary. Okay? And then for Sn1, we want weak nucleophiles. So we still want nucleophiles. We don't want these non-nucleophilic bases, but we want a weak nucleophile like H2O or methox or methanol, all that stuff. Whereas Sn2 prefers strong nucleophiles, such as OH negative, NH2 negative, most things with a negative charge. And then Sn1, sorry, prefers polar protic solvents, and Sn2 prefers polar aprotic solvents. Okay? And so these are the big differences between Sn1 and Sn2 and how we determine if a reaction is going to be Sn1 or Sn2. I'll give you guys a couple seconds to digest this, and then we'll get into sort of a little example. Okay. So let's say I have this guy right here. So let's say that our leaving group is going to be chlorine. Doesn't matter. Remember, the leaving group does not determine whether or not it's going to be a Sn1 or Sn2 reaction. So let's say that we have H2, or not H2O. Let's say we have OH negative in methanol. So when I look here, when I'm trying, and then I see our product is just going to be this, because it's just going to be a substitution reaction. And they ask me, is this going to be Sn1 or Sn2? The way that I do this is I first start with this substrate. So this is our substrate. We can see here that this chlorine is attached to a secondary carbon. The secondary carbon, it can either go for Sn1 or Sn2. So then we go on to what is our nucleophile. We see here that OH is our nucleophile, so it's a strong nucleophile. And furthermore, we're in a polar, oh, I'm sorry, this shouldn't be methanol, this should be DMSO. This is DMSO, is a polar aprotic solvent. Sorry about that, but DMSO and DMF are sort of notable polar aprotic solvents that you should know, but DMSO honestly is probably my go-to for a polar aprotic solvent. So now let's go over what we have here. We have a secondary carbon, a strong nucleophile, and an aprotic solvent. So this is going to be Sn2, okay? So let's say that instead of all of this, we had, let's say we had, let me erase that. We had H2O and methanol, okay? Here we see a weak nucleophile and a protic solvent. So now instead of Sn2, this is going to be Sn1, okay? Oh, and sometimes Sn1 is going to have a third step where the, so like in this case, the third step would be this guy here losing one of its protons, deprotonation. But when we're talking about Sn1, we're more focused on the 2 steps that lead up to this deprotonation, okay? Okay, so does that help clear up any questions about Sn2 versus Sn1? Because I know that this was sort of a harder chapter, at least for me, because it's your first introduction to more organic chemistry related reactions. So let's go on one more time, talk about the reaction graphs for Sn1 and Sn2. So if I said, draw me an Sn1 graph that's endergonic, all that means is I want an endergonic reaction graph with 2 steps. And there we go. And so then this dip here, that represents our intermediate, and these 2 hills represent our transition states. The intermediate is just our carbo cation. Okay. So one question that they could use Sn1, Sn2, and those reaction graphs with would be pick the graph that is Sn2 and exergonic, and you know, oh, Sn2, that's 1 step. Exergonic, that means the reactants are going to be higher in energy than the products. So our graph is going to look like this, okay? And so then you would just do process of elimination or whatever if you're doing a multiple choice test. All right, and finally, the last thing I want to talk about today is the stereochemistry. So this is a little bit more cerebral to understand, but if you think about it, Sn2, it happens all in 1 step. So we can see here that when it's all happening in 1 step, our nucleophile is going to be fighting for space with our leaving group, okay? And all that means is the nucleophile is going to come from the back because the leaving group is forcing it to the back, okay? And so then what happens is you see, in this case, the Br was on the right side, the nucleophile ends up on the left side. And another, so in this case, they become complete opposite, and stereochemistry is inverted. So if we start, like let's say this guy was R, and if we start with an R, and then we do an Sn2 reaction, we're gonna end up with S, and vice versa. So let's say that we have this guy right here, let's say that Br is on a solid wedge or nucleophile, I don't know, OH negative. It's going to come in, replace that Br, and it's going to end up on a dashed wedge because it's opposite to the Br, okay? And we invert stereochemistry. Okay, so Sn1 is a little bit different because remember we have that carbocation. And recall that carbocations are sp3 hybridized. I mean, not sp3, sp2 hybridized, because they only have 3 bonds. They only have 3 electron groups around them. And when you're sp2 hybridized, that means you're trigonal planar, which means this guy is open to attacks from either side. So in this case, stereochemistry is both inverted and retained. So Sn1 can end up with both enantiomers, where Sn2 ends up with 1. So let's say that instead of having OH, we have H2O with Br and everything. And we will end up with, let me just make that a solid wedge. We'll end up with both OH on a dashed wedge, like we did with Sn2. But then we're also going to end up with OH on a solid wedge. And we're going to make a racemic mixture with, just a reminder that a racemic mixture is just a mixture of 2 equal amounts of enantiomers, okay? Does that all make sense so far? Again, this specific thing that we're talking about now with the stereochemistry after Sn1 and Sn2 does not determine whether it's Sn1, Sn2. Sn1 or Sn2 determines the stereochemistry, not the other way around. Okay, but if I were to give you an equation that was like, let's say we go from, I don't know, this guy, and my only possible product was this guy. And I was like, well, is this Sn1 or Sn2? You would say it has to be Sn2. a further question they could ask, they could be like, what possible nucleophile did they use? And they would give you a list of like 3 weak nucleophiles and 1 strong one. So let's say they give you H2O, MEOH, and then ETOH, and then they give you OH negative. You know that the only one in this list that's a strong nucleophile is OH, and the strong nucleophile forces it to be Sn2. So that means that this guy is going to be our nucleophile. Okay? All right, so I think I'm going to go ahead and end it there. If there are any additional questions, feel free to message me on GroupMe or through web courses. So yeah, I'll see you guys next time.